nice conference, and I directed some organizers for workshop ongoing. So today I'm talking about this, which is based on the joint work with Justin Cady at the University of Washington, Yuji Tachikawa at the IPMU, and Kazuyo Nekura is at the Tohoku University. Okay. So I'd like to talk about string theory in this talk. I think string theory slash quantum gravity in this conference. And there's a very important and widely believed in the community conjecture, which is that there is no global symmetry in quantum gravity. Okay, and so there are various reasonings. This is just the two highlights of papers, but there are tons of and I'm not going into detail as why we believe this, but more I'd like to treat it as an assumption in this talk. And okay, so there is no global symmetry in quantum gravity. So I'd like to assume it. Then why am I talking about quantum gravity in this conference, which is symmetry, global symmetry? So am I disobeying organizers? And no. So this is a point we have to make that. So there's a large implication of like this assumption of the non-global symmetry on the effective field theory. So this is a bit counterintuitively, the non-global symmetry conjecture is a reason to consider symmetry in the context of quantum gravity. Okay, so non-existence of something is not trivial. And okay, so we do not know the full non-perturbative quantum gravity or its string theory. We do not know the full non-perturbative form of it, but have partial descriptions. For example, just a perturbative string theory or effective supergravity theory. And so such approximations are in our field community or the effective field theories. Okay, and EFT, effective field theory, typically has global symmetry, and that might be higher or categorical. And okay, so if you believe the conjecture, the no global symmetry conjecture, then any global symmetry in effective field theory, which is approximation to quantum gravity, is a signal of imprecision. Okay? So that's where we can, in that way, we can spot the imprecision in the approximation. Okay, so then so if we spot such imprecision, we try to improve EFT, and ultimately we want to improve the EFT to the point that it has no global symmetry. Okay. Yeah. And so that's a rough strategy of like improving the approximation, and this can be made more precise. Oh, I mistyped. The buffer, of course, buffer, and sorry for that. It was made precise by McNamara and Buffer as a no Bordism conjecture, which is a better way of stating that there's no global symmetry. That's a refined notion, and that I'd like to talk about.
Question?
Yes.
Does the no global symmetry extend to non-invertible symmetries? The no global symmetry conjecture in gravity, does it extend to non-invertible symmetries?
So that's, yeah.
Because it's about charges, right?
Yes. So it's about charges, and yeah, my personal opinion is yes. I think there are a few papers also about that. So because if you do not assume the no global symmetry conjecture for the non-invertible ones, then kind of like if you have non-abelian discrete symmetry in EFT, then you might gauge it and remove the invertible symmetry, and that sounds too cheap. So, yeah, that's one reasoning to believe that the no global symmetry conjecture even for the non-invertible case. In this talk, I'm not going to talk about non-invertible symmetry at all, sorry, but yeah, generally, yes. Okay, so yeah, so the main result is that we claim that there are new Branes, extended objects in heterotic superstring theory, and we use Bordism classes to detect the global symmetry of supergravity or heterotic supergravity or part-additive string theory, and so that we can explicitly found non-trivial Bordism classes in such supergravity, and then to cancel such Bordism class, we propose to introduce or assume some new Branes, and basically that's charged under that Bordism class, and we also propose a Walsh theory of a string Walsh theory that going around those assumed new Branes. That description is very similar to the little string theory around in NS5 Branes, you know it. Okay, and that I'm going to talk about. Also, this Walsh theory defines a non-trivial element of the TMF by, if you believe the Stoll-Stackian conjecture. That motivates usually my collaborator to work with and accomplish the work that Mayuko talked on Monday. Yes, I will also briefly talk about the connection to the Michael's talk. Okay, so that's the summary slide. Yeah. Any question? If not, I proceed to explaining about no Bordism conjecture by McNamara and Waffa. Okay, so we'd like to think about the quantum gravity, but we do not know what it is. So what we can talk about is a weakly coupled effective field theory, like supergravity theory that's contains some fields, a metric or Caban field, gauge field, the atom scalar, and RR fields. Blah, blah, blah. So that depends on your choice of quantum gravity and EFT, but that we know. Okay, and also EFT also contains Branes, I would say. So there's some extended object, or in this, for the sake of this talk, you can think it as some singularity type. So that's where, yeah. So typically these Branes caps some, yeah. So this picture is the sphere is just a ball linking with the brane, and we can regard this a singularity type brane, or singularity type is the one capping the this sphere in the Bordism category. I'm going to talk about explaining it later as well. So I'd like to call the S the geometric structure of EFT as the collection of field, these backgrounds and Branes. Okay, so I'd like to assert that I'm not talking about the dynamics in this EFT at all. I'm treating all the existent fields or Branes as a background rather than dynamical stuff. Okay. So okay, then we consider the Bordism group depends.
Are you fixing dimensions of the Branes, or are you allowing them to vary?
Okay, yes, yeah. So the one important one important parameter of Brane is this n. So the dimension, the codimension of the Brane. Yes, I also fixing another data of Brane is this B. So this Brane caps some sphere, but with some non-trivial, typically non-trivial structure. So that this sphere is not nullable if you ignore the Branes. Okay, so that's fine. Okay. So then we consider the Bordism group depending on this background, so some structure, geometric structure, including singularity types coming from Branes. And so this is a rough picture that, I mean, B is a particular structure, and that might contain the singularities, and of course the Bordism also contains some Branes. But yeah, picture. And okay, so then let's assume that there is non-trivial Bordism class in this Bordism group. And then we can define unendable defect by connected summing. Okay, so this is like, so let's imagine that this is a sheet of the flat plane of the space-time dimension 11 or 10. It's the ambient space of string or emissary, and then along some we pick some d minus n dimensional submanifold, and along it we just connected summing. So at the point we connect some this non-trivial Bordism class and extend it along some d minus n dimensional subspace. Okay, so we can. So this is some geometry, but then there's no. The Bordism class being non-trivial means that there is no deformation that you can make, or so that this defect, the new defect coming from the connected summing, ends. Okay? So that's. So you can count. So if you had such a configuration, like geometric configuration, and then so I assume that these connected sum manifolds are small, and then this X, this gray subspace looks like some kind of defect which is unendable. And then you can count the number of defects, and that's a charge. That's a global charge. Okay, so this defect is unendable means that in particular this number of defects conserves along time. Okay, so that's a conserved charge. Okay, and that's a global charge. That's a higher form global charge because this defect can have more than one codimension, and that we do not like. So if you believe in no global symmetry in quantum gravity, then the Bordism group, depending on Bordism group with this structure equipped with the quantum gravity, full quantum gravity has to vanish up to the ambient space-time dimension. And okay, so that a typical EFT like supergravity does not satisfy this. So what to do with such Bordism class and one. Okay, so if you spot such non-trivial Bordism class, there are two ways out. One possibility is that this charge is gauged by an unknown field or by an unknown coupling. But this way of like just gauging the symmetry, as I commented, typically for discrete classes, typically ended up with another symmetry, and so for this to be, so when this class is discrete, more possible way out is to assume some new brane that caps out this non-trivial flux. So this is a picture. And so in particular, in this talk I focus on the case that this manifold, the underlying manifold is just a sphere. Okay, and but which is not null-coordinate because of the background on it, or flux, if you like. So the most primitive example of this is the D brane. I mean, so back to the Polchinski's discovery of D brane. What he said is that there is so because there is a RR field, and which so you can put RR field on SN so that this sphere can shrink. At the point, then the Polchinski said that there should be a charged object, which is D brane, under the RR field. Okay, so, yep. So that's this line of reasoning is a generalization of the line of reasoning that Polchinski had to discover D branes. Okay? But here I'm not talking about the R. So the only difference is that I'm not talking about the RR flux, but more exotic background on the sphere. Okay, so we found the discrete fluxes in heterotic strings supergravity, and that we think indicates new branes in the heterotic supergravity. Any questions so far?
Actually, I'm confused about the dimension formula. Maybe I'm misreading. I'm assuming the sphere is a linking sphere for the brane, but the dimensions don't quite add up.
Okay. So the P, yeah, I'm not good at matching dimensions.
Konstantin, I had the same confusion, but a P brane is P plus one dimensional.
Yes, that's one source of confusion, yes. P,
I see. But
yeah,
that makes it worse, not better, I think. Anyway, okay.
Yeah.
But that's the idea. The SN is a linking sphere. Is that what's
yes. Yeah, I cannot change that terminology at this point. Yes. Yeah. P means that the dimension of space, not space-time. In other words. Okay. And okay, so then I'd like to describe the Bordism classes in a heterotic string. Okay. So I'm talking about heterotic super string supergravity, and so it has of course metric and Coulomb field and diaton, and on top of it there's a non-trivial gauge field, and it's known that the gauge group has to be either E8 or spin 32 via the Schwarz anomaly translation. But here we would like to know a bit more precision, and what's now believed is that the global form of gauge group is in the EH case, it's E8 times EH symmetric product. The Z2, the Z2 just flips the two E8s. So in other words, this isometry of E8 is another global symmetry, and but we assume that it's gauged. Or this for the spin 32 case, I mean, it's usually called the SO32, but the actual global form is spin 32 mod Z2, which that is not SO32. Now, okay, so we constructed a not null-coordinate G-twisted string structure, which is just a combination of the gauge field and the Coulomb field, satisfying the modified Bianchi identity on sphere of some dimension. Okay, and then from that we like to propose the existence of new p-brane. Not all of them are new, by the way, but some of them are new. And so we found this for n equals to 1, 2, 4, 8, which is power of 2. I don't know why we found nice classes for power of 2, but the fact is it's power of 2. And so the correspondingly we found that p equals to 7, 6, 4, 0 branes. Okay. Some of them are new. Okay, and this case is subtle. Others are this Bordism class is Z2 Z2 class. Okay. So that's a summary of the result. Let me describe this these fluxes of Bordism classes one by one for these cases. So it can move. Oh, okay. Okay. So first I start with this one because this one is maybe most unique. Okay. So as I said for the SO32 string, the global group is spin 32 mod Z2, which that is not SO32. Okay, then as we can notice, there is a vectorless flux on S2, or otherwise there is a non-trivial bundle. This bundle, because of the pi 1 over S2. Okay, so this is an explicit flux that you can choose, and okay, and it's easy to conclude that this is this bundle is not deformable into trivial bundle, and indeed the obstruction is this, just coming from the pi bundle of the gauge group. Okay. So we can interpret this as like the seven form magnetic symmetry in this effective field theory. And so yeah. And so this should be broken by Branes, so that magnetically charged on the gauge field. So that's this is the motivating example for us, that noticing that this this class has to be broken by magnetic brane. Okay, and other examples. So I also present other Bordisms. So another easy one is just E88 heterotic string, and we consider the S1 with the say bounding structure. But then we can twist. So we assume that the Z2 acts on non-trivial. There is a zeta non-trivial acts on E8 times E8. So at the point the trivial E8 bundle, but along the circle we can twist the E8 as we're going around this. So that's also obviously a non-trivial Bordism class, which is Z2 class. A bit more intricate one is four brane charge. So that's on S4. So we put E8 instanton background on S4, and we can take this configuration to be the homogeneous along S4. So there's a homogeneous instanton on S4. And then Bianchi identity of Cameron field, or in other words, we are talking about not just the gauge field, but this twisted string structure, and that the fact enforces that this instanton number sums to 0. And also the Z2, if it acts Z2 on this background, of course it exchanges the instanton number. Okay, so So you can consider the S4 with instanton charge n minus n, and using z action you can trivialize this this structure, or you can find the new Bordism of this for this structure. So I first split that. So I assume two instantons for each factor of E8. I split it to the two S4s with so supporting a single instanton on each. Then I act on one of S4, I act on this Z2, exchanging the instanton number and then going back to getting vanishing instanton number on S4, which is of course nilbordant. Okay, so this S4 2 minus 2 is nilbordant, but half of it is not. So you can do this trick with this. Okay, so that defines a Z2 class. Okay, and okay, so for this case, we expect the brane corresponding to this class, but actually the corresponding brane is already proposed in the emissary heterotic emissary. That is like the open M5 bridging M9. And, well, I should have said. Oh yeah. Okay, so let's comment. Lastly, there's a zero brane charge. So there's a flux. We can for this heterotic string we can consider the flux on S8. Because there is a fourth order Casimir in SO32, and we can find a flux that supported on S8. Okay, so this looks easy, but we have to recall that there's a Green-Schwarz coupling that connects the Copeland field to the particular this flux. Okay, so just putting this on S8 is not consistent, and so we need a fundamental string to cancel this induced Copeland holonomy on this Copeland field. Okay, so the picture, so in this case, picture is this: like you have S8 and put the holonomy, but we also need the fundamental string that going in this direction, stretching in this direction, and it's time. And then this zero brane corresponding to this Bordism class is the boundary condition of this fundamental string. Okay, and this zero brane is the boundary of fundamental string, which is actually proposed by Koczynski in 2006. So yeah, this is also not new, but we recovered in a uniform way. Okay, so any questions so far about?
I missed the part about how you know that the gauge group is spin 32 over Z2 rather than SO32. Is it just from the degree 10 Bordism group has to vanish, or?
Yeah.
Sorry, degree 11 it would be.
Well, so the fact, yeah, I didn't. Okay, so we do have spinor representation in the massive string.
Just by looking at representations. Sure. But that doesn't necessarily fix it completely, right?
Yes. So that leaves us a possibility of either the simply connected one, or this one, and okay, and yeah. So the strings, but the fact that there is no vector representation in string spectrum, part of the string spectrum. I think it states that this one is the correct one, but I do not have concrete, I mean, more exact argument against the other possibility.
Do the results then change completely if you use the other possibility?
Yeah, then there's no such flux.
If I recall correctly, the perturbative string spectrum is now, it fits only with that global flow.
Ah, okay.
Yeah, for all of the perturbative spectrum, yeah.
Thanks.
Okay, so this, like, we found these classes by hand. It's better to do more systematic. Okay, and for E8 case, right after our paper, Aaron DeBry submitted a paper about doing the systematic computation of algorithms using E8 heterotic string. Also, the UG and Michael's paper asserted that if you assume search-like conjecture, then the Bordism classes of heterotic part of the string theory is by a conjecture is classified by TMA classes or equivalent version. Okay, and so there are other classes in their list, and so that indicates other branes, but I don't have. I cannot say anything about other classes. Okay. So then I'd like to. To describe the worldsheet theory in the throat of this assumed new branes. And the prototype is a little thing, so that's for the NS5 brane. That's a magnetic brane, the brane magnetically charged to the carbon field. And okay. And so the near horizon geometry of this brane, okay, or the supergravity solution, is this. This is very well known. And so this is the string where the string goes around. And so this is a picture. We have a brane here in this case, NS brane, and the geometry, the metric looks like a throat going to the singularity point, and the near horizon limit means that I cut this trumpet part, and the geometry basically looks like just a cylinder. So I'm talking about this cylinder part, okay, and worldsheet theory in this region is described by R1, 5, which is just a perpendicular flat directions, and RY phi. This is this direction towards the brane, and this phi means that there's a non-trivial diatom background. Yes, there's a modulating coupling, in other words. Okay, and this paper thought that the other there's another part on the worldsheet, which is SU2 level n current, or the SU2 level n current. And the way this comes out is that, so for the case of NS5 brane, we are talking about the corresponding Bordism class is S3 with the H flux, the flux for the V field, carbon field. And in this case, we put n unit of that, so that's Z class. Okay, and okay, so this is a string manifold, and we can construct the sigma model, the 2D n equals 0,1 sigma model, and that's believed to be RG flow into the fixed point, which is described by this affine Lie algebra. Okay, so that's a that was this sorry so that's the story, and okay, and the central charge is this linear diatom is such that this whole thing has a critical central charge. Okay, so that's the little swing story. Oh, okay, so we try to generalize this to our configuration. So basically we replace this Bordism to other. Okay, and as I said, so starting from the 6th brane case for the spin 32 is one to understand. So in this case, instead of the Coulomb field flux, we have the gauge field flux, and we can choose the SU16 preserving one. That's the most symmetric one. And okay, and as for the supergravity solution, this is just flux for the Cartan of SO32, so you can regard it as just abelian gauge field background, and such is already described in Horowitz and Strominger. So that's just we cited. That's exactly the same as the Lichtenstein case. I mean, almost the same as Lichtenstein case. And we take QI to be just half. So this preserves the U16 modulo Z4 inside its spin side. So we again for the supergravity we again have this kind of picture. Like we have the assumed new brane here, and there's the throat region. So this is a near horizon region, and we'd like to think about the string Walsh theory that lives on in this region. Okay, so again, the Walsh theory should be something like the flat direction, the perpendicular to this picture, and this direction. And so in UV we use the sigma model. We target this. Okay, but we like to assume that this flows to some CFT, and the assumption is that CFT is the right one to use as a Walsh theory. Okay, so this angular and gauge degrees of freedom as a 2D QFT can be described like just S2 target sigma model with n equals 0,1 supersymmetry, and tensor with this Lie algebra, affine Lie algebra SVOA, but tensor with the flux. I mean the twisted tensor because of the flux. Okay, so the question is what is IR fixed point of this 2D theory? And to determine that, we use the 2D CFT duality, which is known, that the spin 32 over Z2, level 1 is dual to SU60 for level 1, and tensored with this free fermion, the Majorana fermion, the two of them, and gauged by the left moving fermion number. Okay, and the flux is such that we can study how this flux translates into this language. And what we find is that this additional fermion factor behaves exactly as the tangent of S2. Okay, so this part, the 0,1 and this fermion is actually comprised to n equals to 1,1 non-chiral supersymmetric sigma model and the remaining factor, which is as before. So that's what I've said. Then the semi-classical analysis tells us that this kind of S to the target sigma model RG flows to just a two vacuum breaking the left moving fermion number. So then we are gauging it. So just cancelling the numerator and denominator. The RG flow fixed point should be this holomorphic CFT. Okay? This is a holomorphic spin CFT. Okay, so we propose that the string, the worksheet of string is a linear diaton theory tensored with this particular holomorphic CFT. Any question? And so we found a very nice pattern for like the Bordisms that we found. And so I've told you the 4 cases, and so E and S stands for like E8 times E8 or spin 32. And there's a very nice pattern of 2D CFT duality, or like of this form, where like G1, G is E8 symmetric Z2 or spin 32 module Z2, and H is in these cases like this, and then N is A. Okay, so we substitute this duality to here, the sigma model. Then what we get is, so again we can check in all cases the flux is such that this additional fermion part, the left moving fermion part is transformed as a tangent bundle, section of tangent bundle of Sn. So that gives us n equals to 1, 1 sigma model, the sphere sigma model, and then n comes with the additional factor and gauged by the left moving fermion parity, and the semi-classical analysis again tells that this has two vacuum breaking the fermion number and cancelling out, and we get this holomorphic CFT described by the affine. Yes, also we propose that the unified proposal is a worksheet for this class of worksheet of Branes corresponding to this class of Bordism classes. Classes should be described by this theory. Yeah. Is there any question? I think I have plenty of time. So.
Maybe you're probably going to comment on that, but what is the central charge of this HK?
Yes, so those are the, HK is, the same as, the central charge is 32 minus n. 32 minus, sorry, central charge is the half of it, 16 minus half of n. Yeah, so that's this. Oh, sorry, this should be n. So n equals to, so other than zero Brane cases, I'm not sure. These are in the, also at this I and UG believes that it gives a non-trivial class of TMF by a Stokes-Tankian conjecture. So the fact that like the sigma model gives rise to a TMF is a matter of the TMF orientation of spin Bordism. But in the context of cyclic conjecture, we can also talk about the RG flow of the CFT of sigma model to some CFT, and that's we found that at least there is a deformation to a purely homomorphic CFT, and that's a vortex operator. So that's well described by vortex operators superalgebra. So this is mathematically defined context. So as Mayuko also pointed out, that it will be very interesting to find some map from the VOSA to TMF. This thing is not expected to form a spectrum, so that's probably the hard part. Anyway, that'll be a well-posed question, I think. Okay, and I also comment about the pairing that Mayuko talked about. I give the physics interpretation. So Mayuko introduced the pairing and of the TMF and Bordism. I hope I haven't made any mistake of the statement. And so we say that these theories gives rise to the TMF classes. Yeah. Okay. Yeah, this is torsion pairing. Yeah, it should be. I should have said the torsion. Nice. Yeah, this is torsion pairing. Sorry. Yeah, and yeah. Anyway, these are torsion classes, and then so there's a pairing, and in this pairing is the way they checked that these TMF classes are non-trivial. Okay, and physically this pairing gives you the theta term. So of the compactified theory, string compactification, using this theory or this geometric background. Okay, so this part is a 10 minus d dimensional manifold. And so you evaluate the theta term on the compactified string theory, and that gives you distortion. So that's the physics meaning of the pairing. So the summary. So in this talk, I just assume that no global symmetry in countergravity. And that is an important constraint on effective field theory, and McNamara and Buffer put in a nice, more precise way of stating the same. So, and we found the non-trivial heterotic string structures on spheres with a power of 2, where the Bordism class is seemingly non-trivial, and then so we assume that that should indicate the new brane, and we also constructed the worldsheet theory around the throat region of new branes for these dimensions of branes, and that worldsheet theory has a uniform form of this kind, and this HK are the particular holomorphic SQs, the below essays. Okay, so there are many questions. So one is that this is strongly coupled in the sense that this diatom grows up at the brane. So this is very non-perturbative description. So we cannot do any computation in this good to have weakly coupled version. So so the NS5 brane case is such. So there's a way to cap out this float region in other words, and so that will be desirable to generalize their construction to our case. Also for the spin 32 case, there's a S duality to type 1, and if you analyze it in type 1 description, the type 1 string coupling seems to be weak after taking SUO. So it's puzzling that we cannot find some perturbative distribution in type 1, but we couldn't find so far. And of course, thinking about other Bordism is also important. One prominent example of non-trivial Bordism is type 2b, and type 2b there is no known boundary condition for end of the ball brane in type 2b string theory. But if you believe McNamara buffer conjecture to the point that n equals to 0, then there has to be end of the ball brane. So those are purely physics questions, but there's also, I'd like to state like the potential place that the physics and math might work together well, and that's trying to say something about the structure of fluid quantum gravity in somewhat universal way. Okay, so McNamara buffer is conjecture is this. So one quick question is that from just this statement, can we constrain S? But we are allowing singularities. So if we allow any kind of singularity, then Bordism is trivial. So that's too quick, and we have to come up with some kind of come up with a constraint on Branes singularities, and also in this discussion we haven't really talked about topological coupling in the constraint coming from topological coupling, so that should also be included. That I do not know how to do, but so that's still the answers needs to be. Questions needs to be answered by physicists, but hopefully this framework of talking about the Bordism of the fields and singularities it might be useful place to talk with each other. That's my hope. Another comment is that recently people have been highlights that this Branes has topological degrees of freedom on net in very the limiting situations. So that's, I think, indicates that on Branes we really have to thinking about the non-invertible structure that realized by these topological non-trivial topological degrees of freedom. Lastly but not the least, I'd like to mention about the series of works by Fiorentina and Satya Schreiber, and I apologize if I missed any other authors. And they have, well, they also have a series of papers about the structure of M theory and try to nail down every detail of it, I think. And also, so that's pretty much related. But so that's. And I'd like to say that they are the first ones to really thinking about the higher structures in the string theory context. So there should be much to learn. Okay, so I stop here and thank you for your attention.
About what happens if you put the this thing on a circle, then the two are T-dual. Do you get some map from these structures?
Right. So yes, let me recall. This example. So yeah, here I'm talking about the bounding spin structure, and well, we could also talk about the non-bounding spin structure. But for bounding spin structure, first this is non-supersymmetric background. So yes, of course we can take the T-duality, but then we have to study the T-duality in the non-supersymmetric background. And I think in this case, this thing is T-dual to the EH level to non-supersymmetric heterotic string. And that's consistent with this thing, the CFT of this thing flows to EH level 2. So yeah. That's kind of, it's not always that the EH goes to spin 32 in the non-supersymmetric background. Yeah, but that's a nice point of like I think we should study this T-duality in the non-supersymmetric background, which is not really well explored. And that includes all of the non-supersymmetric heterotic strings.
The interpretation of our result, maybe in the in past. So this why so this slide. So why do you? I'm confused about interpreting our paper. No. This is not the case. Not the slide I was referring to. The what the minor. This one.
Yeah. Okay.
So why? So this uses so this is maybe you want to say that this is the consequence of the pairing I described, which comes through the Anderson self-duality. So could you?
I think there can be precision. Yes, I think.
Why do you? So Heterotic.
Yeah, I just meant that the sigma model defines the content here.
So I think that the correct statement is that there is a map from left to right. I think because the pairing. So the fact is that TMF and KO divided by TMF is Anderson self-dual. This is very close to the duality, but you also pull back to spin string relative Bordism. This is not isomorphic.
Oh yeah, I think I'd like to think that this is a more like better version of the Bordism class that I described. Rather, so here it's more like we are directly talking about the 2D CFT, which is not necessarily a sigma model. So yeah. Well, I think I can have some imprecision in this.
I am often asked by people that can you do similar things in the case of other supersymmetric, so the type 2B, type 2A. I have really no idea about. Do you have some opinions on maybe classifying that things also by some spectrum?
I have an idea. Yeah, should we?
Some kind of spectrum.
I mean, it should be like coming from space of n equals 1, 1. N equals 1, 1 SQFTs. Not sure that forms a spectrum. mean, I do not know the nice grading even. So yeah.
Any other questions?
Can I ask you a question? Related to the pairing between TMF and Bordism? Is it for both spring and spin in your structure?
Sorry.
You wrote that you have a pairing, right?
Oh yeah. Spin for. Okay. Yes.
You have a pairing for both spin and spring, or?
Yeah, the pairing is.
This is relative spin Bordism, spin string Bordism.
Yeah.
Okay, thank you.
All right, so if there are no other questions, let's thank Kantaro again.